Hello, my name is Chatterjee and I am giving you this talk from IIT Kanpur. Let me just tell you a little bit first about this talk, and what I will do is I will use this black marker to navigate the talk. Okay, so this is on preliminary experiments. It is an optimization problem which is relevant to the conference. This is the talk I am giving for this conference in BIT Mesra. My name is Anindya Chatterjee and I am in IIT Kanpur. This optimization problem involves matrix eigenvalues. Preliminary experiments, because this is the first time I am playing with this problem. The problem is simple to state, it is difficult to solve, it is scalable. That means we can increase its size without thinking too hard, and the problem becomes very much more difficult, and it has constraints. Normally in a conference we are able to meet face to face and get to know each other. Since over here we can't, I will take the liberty of just giving a small description of where I am from. So here I am. This is the IIT Kanpur web page. It is interesting. Right now the timing is such, our PhD admission advertisement is out. The deadline is, if you see here, the deadline is April 4th. So those of you, if there are any people in the audience who are interested, they can look. We have several departments here, engineering departments, biology is also here with engineering, aerospace, mechanical is here. This is my home department. Our humanities has been split into economics and humanities and social sciences. Within our sciences, we have chemistry, mathematics, statistics, physics, as well as earth sciences and cognitive science. We have a separate industrial and management engineering department, and several interdisciplinary programs, including one in photonics science. Okay. Now, if you go to the mechanical engineering department, we have approximately 40 faculty members. That's my page over there, and within this page, I maintain a separate home page that is here. In case you go, so now you can see a picture. It is like I am facing you. There are things on my web page that some people may be interested in. For example, the difficulty on academic publishing, an article for young people trying to publish. Maybe some members of the audience may be interested. Some people may like mathematics problems, computational problems over here. On this one, I call it Dilbert's problems. It's a small joke related to Hilbert, because Hilbert's problems are very great. This is on transferable skills in core engineering. This is my critique of our joint entrance exam, which I think does some damage, and so on. So I also have the PhD thesis of my students over here on this page, in case anyone wants to look. And I have written a book recently because I am troubled by Indian demographics. There are too many colleges, too few jobs. So this one is called Build and Sustain a Career in Engineering. It is available in case anyone wants to take a look. Okay, so that's the introduction to me. Let us go to the talk now. The talk is here, and I'm going to use this marker pen. So as I explained, it's in this optimization area, although I am actually a professor of mechanical engineering, primarily interested in dynamics and vibrations. But I have an interest in optimization for reasons which I think will be clear soon. So I am not an optimization theorist. I don't develop theory. I am a user, and I find the idea of optimization helps me obtain acceptable solutions sometimes. It is good for design, not for necessarily finding a truly optimal solution, because optimization is for an objective function, and we don't know what the best objective function is, right? What is the best car or the best pen? We don't know. But nevertheless, when we have multi-criteria, there are efficient frontiers, there are fabulous aspects of theory. And then after that, you still have to choose some solution, and that solution may be acceptable. This is why I am enthusiastic about optimization, and I am happy to give this talk to get this opportunity. Okay. Now, one of the things that make optimization interesting is that if you have complicated constraints, if you have a lot of local minima, if the problem has high dimensionality, then solution can be difficult. This is where there is something to be thought about, otherwise it would all be straightforward. So to think about them, we often use something called benchmark problems. These are standard problems. There are several such problems. They have differing levels of difficulty. Students may implement several optimization programs. Maybe I should change the ink here and use red. Okay. To solve these problems, and they report the statistics of how successful it was, how long it took to run. Sometimes the solution package has some parameters, so they try to understand what those parameter values should be. So when you think about these benchmark problems, then you realize these problem statements must be easy to understand, right? So you cannot have optimization of air drag on a fighter aircraft, because the person will have to learn a lot before he can implement that. The problem should be easy to understand, easy to code. They should challenge the optimization method, right? And success should not be guaranteed, right? Then it makes it an interesting benchmark problem. And as computer capacity increases, the problems must be able to scale up so that they can keep challenging the computer, right? So, x squared plus 2, what is the minimum? This is not challenging, you know the answer, right? So there's no point, okay? Or linear program with 6 variables. Any computer can solve this now. There's no problem, right? So the problem must scale up also. I hope you agree with my assessment of what these problems should be like. And with that viewpoint, I offer the contribution of this paper. I propose a new benchmark problem. The problem is simple to state. It has a nonlinear, non-smooth constraint. Okay. It has many local minima. It is difficult to solve using generic algorithms. Okay, so whatever it is, you can try genetic algorithm, simulated annealing, F-min search, whatever it is fairly difficult to solve. The function evaluation for this problem is quick, so that is good for experiments, right? If you want to run it thousands of times, tens of thousands of times, it's useful. The problem is arbitrarily scalable. You can make it as big as you like, okay? And the answer is known for all problem sizes, okay? So this is the problem statement. The problem statement is you choose an integer n greater than or equal to 3. Why 3? Arbitrary. Okay, the design variable has n square elements. So for example, if n is 3, then x, x1, x2, x3 up to x9. 9 is the square of 3. Okay, so the problem can in this way be 9-dimensional, 16-dimensional, 25-dimensional, or as big. 25 square equals 625-dimensional, anything like this. The constraint is that the sum of the absolute values of the element should be less than or equal to 1. So you will notice that this is a non-smooth constraint. It is not differentiable at many points. Okay, now what we do is we arrange the elements of x in a matrix A. Okay, so how does that work? So for example, in this case, what we would do is x1, x2, x3, x4, x5, x6, x7, x8, x9, right? Similarly, if there were 16, then A would be 4 by 4 matrix, etc. Okay, so what we do is we arrange the elements of x in a matrix A. We compute the eigenvalues of A using a computer. We don't do it by hand, of course. We arrange them in order of decreasing magnitude. So we arrange the eigenvalues as lambda 1 magnitude, absolute value of lambda 1, absolute value of lambda 2, absolute value of lambda 3. The idea being lambda 1 magnitude is greater than equal to lambda 2 magnitude is greater than equal to, and so on. Okay, and we choose the third eigenvalue just to bury it a bit deep. Okay, and we maximize that magnitude. This is the problem statement. Okay, so here is the variable, here is the variable, here is the variable, here is the constraint, here is the objective function, and we are supposed to maximize this. This is the optimization problem that I put before you. Now there is a theoretical solution. Okay, so I can put 1/3, 1/3 and 1/3 on the diagonals. Then this is the all the other elements can be 0. Then the sum of xk absolute value is equal to 1. So it satisfies the constraint. The eigenvalues are 1/3, 1/3, 1/3 and 0, 0, 0 and so on. So the function, our objective function, is 1/3. Okay, it satisfies the constraint. It gives an optimum of 1/3. I have played with this problem quite a lot. I have never obtained a bigger value. I don't believe there is a bigger value. We could have 4 diagonal elements each equal to 1/4. Would that be a local optimum? I will show you. I think it can. Okay, now let's say we take a random matrix Q, n by n. The new matrix Q inverse AQ has the same eigenvalues, of course, but what happens is that this constraint is violated. This constraint will typically be violated, and so you will have to lower the eigenvalues, and in this way you will not achieve 1/3, but you may get close to 1/3. So you may end up in a local optimum that is close to 1/3 but not exactly equal to 1/3. Maybe you'll get an optimum which is 1/4 or close to 1/4. Maybe you'll get an optimum that is 1/5 or close to 1/5. These are things to be seen. Okay, so here is the numerical experiment. For the numerical experiment, I will use one method. Okay, that is MATLAB's fmin search. This is simple. It's one line. Okay, it does not require derivatives, require gradients. It solves an unconstrained problem, but what I will do is I will use a penalty parameter. That one I've just used a large number which gets bigger and bigger, and as n gets bigger. You could try it with other values. This fmin search is a built-in function. With this penalty parameter, I write the objective function in a MATLAB program, and then I use this with initial condition. Okay, so convergence parameters in the optimization, these are MATLAB parameters. The tolerance on x and the tolerance on the function evaluation, I've just given these. You could try with other values. Then we will start with random initial guesses. Okay, so then after we give the random initial guess, we will run it. Then we will reinsert the same answer into the program and run it again. And in this way, we will keep running until progress ceases, until we are no longer getting a better solution. That is the optimal result, possibly a local minimum, but I have not proved that it is a local minimum. Okay, but fmin search is not making progress. At this point, we note the optimal result and we note the number of function evaluations. We can choose n and then repeat capital N times. Let me show you my results. Okay, so no, not capital N, apologies. 200 times is what I will show you. Capital N below is the number of function evaluations. Sorry for the confusion. So let me show you some initial results. Okay, so I've done 200 runs each. Here is n equals 3. All of these, this one, this one, this one, n equals 3. All of these are n equals 4. All of these are n equals 5. So I hope you understand the display scheme. Okay, now over here what I have is function evaluations. So each time, 200 times I have given a random initial guess, I have let fmin search run. After it has run, eventually it has stopped making progress. I have noted down n. So we can think of this n as a random variable. It is a random number of function evaluations, right? So that random number has a cumulative distribution. It has a CDF, right? So this is that CDF here, this curve here. So the median, the 50 percentile value is about here, and you can see that is about 8,000 function evaluations, okay, for n equals 3. For n equals 4, it increases, right? So it increases. For n equals 4, it comes here. This is 20,000, maybe 25,000, something like that, right? So the number of function evaluations increases by approximately a factor of 3. How about here? When I come here for n equals 5, in that case I have 10, 9, 8, 7, about 6, right? So it's about 60k. Okay, so the number of function evaluations is increasing. All right, the objective function obtained, right, that is also a random number. It has its CDF. You can see that this number is pretty close to 1/3, right? But here are all these points which are close to 1/3 but not 1/3, and the function was not making progress. And some of them, like some percentage, didn't do very well. You know, they were near 0. There were some of them were stuck near 0, which is a bit surprising. Okay, this is a scatter plot of the function value against the number of function evaluations. So you will see that this function value or this function value, which is quite small, is occurring at a number of function evaluations that is bigger than some others, right? And you can see that more clearly here for the n equals 4 case. This one is about n equal, this one's about 0.25. It's getting stuck near 1/4. And you can see that even for a large number of function evaluations, it remains stuck there. Over here, there is an approach to about 1/3, but there are so many of them that are close to 1/3, but not quite. There are many that are close to 1/4, right? So here again, you can see that it is getting stuck near 1/4. Okay, with n equals 5, you are getting stuck at places near 1/3, you are getting stuck at places near 1/4, you are getting stuck at places near 1/5. There aren't a significant number near 0. Okay, so this is the sort of result that we have got with n equals 3, n equals 4, and n equals 5. You can see that the number of function evaluations, 8,000, 25,000, 60,000. Let us look at a few more. Okay, so now let us, here are 200 more, and this is n equals 6, n equals 8, and n equals 11. And for n equals 6, you can see that a typical number is a little over. So that's 2 lakhs, this is 1 lakh. I don't know how much that is, maybe 1.2, right? So 120,000. Okay, over here. Now, how much is that? That's 1 lakh, 2 lakh. It's about 3 lakhs, 300,000. Let's look here. And this is about 800,000. Okay, so these are the typical values. These are the median values, right? Because this is a cumulative density function, 0.5 represents the median. Now let us look at the function evaluation. Function values obtained. Here is 1/3, here is 1/4, here is 1/5. Okay, here is 1/3, here is 1/4, here is 1/5, and we'll have to think about what this is. This is drawn with a computer. This is 1/3, this is 1/4, this is 1/5, and this is 1/6. So you can see that it is getting stuck. They are all local minima, but more than that, there is an approach to 1/3. See, if you zoom in here, you will see it is going like this, right? So these are all various local minima or something close to a local minimum. And then over here in the scatter plots again, you can see that it is possible to get a low value even after a large number of function evaluations and a high value after a small number of function evaluations, and the same thing extends here, right? So here we have 1/3, 1/4, 1/5, 1/3, 1/4, 1/5, and maybe one or two here, 1/3, 1/4, 1/5, and 1/6. Okay, so with these results, I can now reach my final slide. These are my conclusions. So I have presented a problem to you. The problem is simple to state, it is simple to code, and the correct answer is known, right? The correct answer is 1/3. Starting from random initial conditions, many optimization routines may struggle. I have only, of course, used fmin search, and it has struggled. Okay, there are many local optima. For larger n, the optimal values bunch up close to 1/3, 1/4, 1/5, but may occur at slightly less than these simple values in this sort of approach that I was showing you in the CDF. So there are many of them close to 1/3 and then again close to 1/4 and so on. Okay, many of them. So I hope that this problem may serve as a good benchmark problem in future work that you may take up or others may take up. For those people who are interested in trying to understand the relative merits of different optimization schemes, this can be a good problem to try. So since this talk is being given long distance and due to some institutional reasons, I may or may not be able to be live during the talk. That is why I have recorded it in advance. This is me. If you have questions and I am unable to answer them, I'm just putting it here. You can send me email and I will try to answer. Thank you very much for your attention.